This lesson is on section 10 of your workbook and referring to refrigerant system charging. Charging a refrigeration system. The correct charge must be added for a refrigeration system to operate as it is designed. Use a scale to determine the amount of refrigerant added to a system. Evaluate the charge either by superheat, subcooling calculations, manufacturer supplied charts, and tables. And I might add that guessing is not going to work here. Vapor can be added to the high and low side of the system when the pressure is in the system is lower than the pressure in the refrigerant tank. The vapor can be added to the low pressure side of the system while it's operating. The cylinder may need to be warmed up in order to build pressure to charge the system. There are occasions when the refrigerant cylinder operates at a very low temperature and starts to freeze up on the outside when you're adding refrigerant. Warm water can be used, but once again, do not ever use a torch. Utilizing a torch is going to create a lot of issues here, so please always use warm water. Remember, we want to overcome the pressure differential. Here we have a chart. It's a cylinder temperature and pressure. If you look on the low side, notice here that on this valve here, basically we are hooked up to the low side of the system, and notice that gas will flow if this valve right here is open. So when you're opening this valve on a analog or digital manifold set, what you're going to be doing is admitting refrigerant through the center hose. In this case, we're utilizing R134A, which is going to go through the middle port, and it's going to come into this hose here, which is the low side, and it's going to go right here through the suction service valve into the compressor. Now notice that this valve is not back-seated, front seat. It's what they call cracked or mid-position. Please be aware of that. So that being said, we are admitting, in this case, refrigerant vapor. Notice that the cylinder is in the upright position. Notice that the ambient temperature surrounding this cylinder is 95 degrees. And notice that there is 114 psig in the refrigerant cylinder. Now notice that the pressure up here on the low side is less than 20 psig. So what we're saying is the pressure inside this tank overcomes what is on the low side of this system. That in turn allows refrigerant to go through the low side and be admitted through the system. And of course, this compressor is operating, and as it is operating, it is increasing the pressure temperature relationship to the point where the refrigerant now is compressed and then of course added to the system. The temperature of the cylinder is 95 degrees. The pressure inside the cylinder is 114 psig. The low side is 20 psig. Liquid refrigerant charging. Okay, this is kind of a touchy subject because if it's done wrong, you will destroy the compressor. One thing I've said earlier, I'm going to say right now again, compressors are not designed to pump liquid. When a system has been evacuated, liquid refrigerant can be added through the liquid line service or king valve on the receiver. The low pressure control may need to be bypassed by the use of an engineering bypass wire during the charging process. When the known amount of refrigerant must be charged, weigh it into the system. Liquid refrigerant charging tips. Liquid must be vaporized once it leaves the charging cylinder to prevent any liquid from entering the compressor. When charging systems with blended refrigerants, the refrigerant must leave the cylinder as a liquid. The gauge manifold valve should be used only on compressors where the suction gas passes over the motor windings. In this illustration here, we have liquid refrigerant charging graphics here. So here we have the refrigeration system here, and of course here you got the condenser, here you got the reciprocating compressor. We have our service valves. This would be your suction service valve, your discharge service valve, and this would be the liquid line or king valve right here. And notice that this is where we are adding liquid refrigerant. So what we're saying from the previous slide, we have the ability to add liquid right here at this point, because in this portion of the refrigeration air conditioning system, the refrigerant only should be existing as a liquid at this point anyways. And then of course, if you'll notice, you got a TXV, and in this TXV, this basically you have the TXV mounted on the liquid line. Notice that the bulb is mounted on the line leaving the evaporator coil, and of course coming back in this case to the suction service valve. So on this side of the system, this is your low side, this is your high side. Notice that the valves here, notice the position of the valve. This valve right here is back seated, and notice that we are bringing refrigerant in through here. Notice that this valve is closed because we're not actually adding refrigerant to the low side. We actually got this valve cracked here. So we're bringing liquid refrigerant in through the analog manifold, and of course this valve is open, and now we're bringing it in through this liquid line service valve, and we're adding liquid to this refrigeration system. So by adding liquid to the refrigeration system at this point, then basically we can charge this system. And notice that the valve position, your gauge port is up here, your back seat and mid position, front seat. So front seat down here, mid position in the middle, back seat here. So these are really important to understand these positions on this refrigerant service access valve. If you don't understand front seat, back seat, mid position, I will be happy to explain this to you in the lab environment so you can see how this works. I do have service valves that I can show you and show you what the position is on this. This is very critical, because if you don't understand this, you're going to have trouble trying to access a system. This is not the same thing as a Schrader valve. This is a type of valve which requires the use of a refrigeration service valve wrench. Do not, and I repeat, do not use a crescent wrench. Do not use a pair of vice grips. Do not use a pair of pliers. These refrigerant suction service and discharge valve, liquid line valves have a square head, and they have a specific tool that is required to operate these with. Now, in this system, the system is being charged where there's no refrigerant in it. The liquid will be added towards the evaporator and the condenser. No liquid refrigerant will enter the compressor at this point. Weighing in refrigerant, very, very important, especially if you have a heat pump system. If you don't take and weigh in the refrigerant, you're going to have too much or you're going to have too little. Weighing in the correct charge can be accomplished with electronic scale. Bathroom scales should never be used, period. I don't care if it's a digital type, whatever. You need to have a specific refrigeration scale. Ones that I recommend are one by Fieldpiece. JB makes a very good one, and there's some other ones out there in the field, but they are designated and designed for refrigerant bottles. Electronic scales are often used where they automatically display the amount of refrigerant being removed from the cylinder. Some units dispense a predetermined amount of refrigerant and then shut off. Some units offer features such as audible alarms and wireless controls. So you have the ability, depending on the refrigerant scale that you're using, to monitor this thing remotely. You could actually download an app and monitor it on your phone. I personally don't do that. I actually am at the job site and I'm actually checking the refrigerant charge as we go through it. And then what I will do is monitor. I will actually sit and monitor the amount of refrigerant going in. Typically on most systems that I install today, they are pre-charged from the factory. As far as R410A as an example for air conditioning, And typically, depending on the line length, I may or may not have to add much refrigerant at all. If the line length exceeds 50 feet, you will definitely be adding refrigerant. If the refrigerant line set from the outdoor condensing unit to the evaporator is less than 25, I'd say there's a pretty good chance you're not going to be adding much of any refrigerant. But be prepared to add refrigerant anytime you install or replace equipment. Once again, you need to have gauge manifolds set, such as a field piece unit that will basically take and it will take and monitor superheat or subcooling. All right, graduated charging cylinders. They are used to add refrigerant to smaller systems. They are affected by the ambient temperature. A pressure gauge will give saturation pressure and temperature of the refrigerant. They must be calibrated before each use. Select one that is large enough for the system which will be working. Now, there was graduated cylinders that basically you would add liquid refrigerant from the bottom and you would vent out the vapor on top, and they're technically illegal under the Clean Air Act of 1990. I don't know why they still talk about them, because honestly I haven't seen anybody use a graduated cylinder. When I got into the trade 45 plus years ago, yes, they were in widespread use. But I will tell you this, based on my experience in the industry, I don't know of anybody that utilizes them today. Charging charts. Curves and or charts supplied by the manufacturers used to help properly charge systems. The charts and curves vary for the manufacturer to the manufacturer. Utilizing superheat values for fixed bore metering devices and subcooling measurements for thermostatic expansion valves. Subcooling. I utilize this method all the time. Now, in figure 10.21, the subcooling charging method for a high efficiency split R410A air conditioning system with a TXV metering device. In the good old days, we used a digital thermometer in conjunction with the analog gauge manifold. I think that personally is a waste of time. I now utilize a field piece or Tesco or other brand type electronic gauges that have the superheat and subcooling functions built into the manifold. This requires the use of a clamp for the liquid line and a clamp for the low pressure suction line. So you have to clamp onto the appropriate lines. In this case, for subcooling, you need to measure the liquid line, and basically what you're going to do is look at the pressure. You're going to record the actual temperature of the refrigerant on the liquid line, and you're going to subtract the difference from the actual measured versus the saturation temperature of the refrigerant at that point. And when I say saturation, I'm talking about the PT chart. That means you got to pull out the paperwork, pull out an app. Quite frankly, I'm a lazy guy, and I'll just be honest with you. I'd rather let the digital gauge manifold set do all that. What I love about the field piece, and I know I'm making a big sales pitch for these guys, is once you hook this thing up, the calculations are done for you, and it speeds up the process considerably. I highly, highly, highly recommend that you make the investment in a digital gauge manifold set where these calculations are done electronically. They're accurate, they work extremely well, and they do a good job. So basically, don't forget, on the liquid side, basically you're going to take the pressure reading. You're, in addition, taking the refrigerant pressure reading on the liquid side. You're going to take and convert this pressure to the corresponding saturation temperature on the PT chart. And then, of course, you're going to subtract that from the actual measured, and that is going to be your subcooling at this point. And of course, you have your indoor air handler, you have your evaporator coil, and in this case here, we got return air going in at 75 degrees, and coming out of here, we should be getting a 40-degree coil. Probably we're going to see around 55 to 50 degrees, because we have to add air losses, air temperature surrounding in order for this thing to work. But typically we're going to look at a 20-degree split between the return air going in and the supply air going out. I have seen higher than that depending on the system, depending on the leakage, etc. Charging a near azeotropic or xeotrophic refrigerant blends. Now that gets a little bit more complicated. Blended refrigerants have different properties than component refrigerants. Azeotropic blends only have one boiling point and one condensing point for each pressure. Near azeotropic or xeotrophic blends temperature glide when they evaporate or condense. What we're telling you is this. Basically, what is happening is the boiling point is all over the place on the azeotropic or near azeotropic or the xeotrophic blends. And you have to look at your chart to come up reasonably close. Manufacturer of that refrigerant will supply you with those pressure temperature relationships. But remember, you don't have one boiling point when you're using blends. Dew point value. Where the saturated vapor begins to condense, used for superheat calculations. Bubble point values, where saturated liquid begins to boil, used for subcooling calculations. So, depending on the charging method used, you're either going to use the dew point value for superheat, or you're going to use the bubble point value for subcooling on a blend. And this gets a little bit tricky. Unless you know what you're doing, you need to talk to somebody, consult somebody before you attempt to charge a blended refrigerant in a system. An example of this would be an R22 system which has been retrofitted to R407C. So that would, the R407C would be a blend. And if it has a TXV, you're probably going to use the bubble point value on the PT chart for this. The manufacturers supply you with the charts that you can calculate this. You can also do this on the digital gauge manifold set, such as the Field Piece 360, 460, etc. Fractionization. This is an interesting issue here. It occurs when some of the blend evaporates or condenses before the rest of the blend. If the xeotrophic blend that you've installed in the machine leaks, the component of the blend with the lowest boiling point will leak faster than the other part of the system. It will not occur when the refrigerant is liquid. Refrigerant must leave the cylinder as a liquid. So what we're telling you here, if you charge a system using a blend, 407C as an example, you will charge as a liquid. If you're charging a new system, R410A, you will charge as a liquid. Even though 410, well, it's not a pure compound. It has more than one chemistry designation. You will charge these refrigerants as a liquid. As a side note, when you take and purchase R410A in the pink or rose colored bottle, those bottles are designed for 25 pounds of refrigerant, not 30 like R22 is. Please remember this.